And I think that's already blurry. So to make this not blurry, I'm going to go here. And then it goes back. And then he left is not going to be blurry anymore. Okay, I'm assuming that's clear. Okay. So we're now going to look at both Einstein condensates. And I'll write this down here to see if this works. Both Einstein. And this was actually proposed by Einstein, but he didn't basically know. No one could actually prove it until actually, the like 2000 or so. We got a very quick Nobel Prize, a very well-deserved Nobel Prize. Okay, so before we do this, we have to have a couple background. So some background first. Okay, we have to deal with the dreaded mu. Okay. So, the problem of mu. Okay, so let's figure out what's going on here. So, remember when we did this? We actually calculated the Bose-Einstein distribution. We started off with the partition function. And the partition function is the sum on all states and all n values in that state. And I think we were using ANS because I think we had like an n and then we had an e or something. But I think I used that notation here. Okay. And remember what this is? We have these factors like this e to the ei mu like this over kb. We have these factors here. Okay. And then what did we do? So if we looked at the energy field like this, we could have all these energy levels like this. We could take a particular one. I'll call this e sub I here like this. And what we could say is that what is this? We took the one state here. We said, what is this going to be? Well, this is going to be the number of particles in that state, n sub I, then times the energy of that state here. So maybe this is the energy here, E, but then the actual energy of that state that we have here is going to depend on the number of particles we have here. And we're assuming a non-interacting particles. And so we put this in here. So we had this Ni, E minus mu I over kBt. And we rewrote that as the sum here. Then the sum here now just goes to a sum on Ni. You can pull out all this other stuff. We had that. And we said, oh, well, this is a geometric series. We said that this is really that. Okay. And we did that sum. Remember, the sum goes from basically from 0 to infinity. When we did that sum ends up being this 1 over 1 minus this e to the minus e minus mu over kBt. Remember that? Okay. Now there is a catch here, and here's the catch. If this is an infinite sum, what do you know about the exponential term? The exponential term had better be something if it's a geometric series and then converge. That term had better be less than 1. It has to be less than 1. So the catch here is that this term here has to be less than 1. Okay, and this is for all E and T. Okay, so let's put this over here. What I have here is that this guy here is here for all E and T, which is just what I have there, but I'll just isolate it, including when is 0. Right? Has to be true for any value. So what this means here is that we have this this guy here, so the minus minus make a plus. That has to be the case here for all t. Well, there's an implication here. From this right here, therefore mu must be negative. Okay. And so what we want to start doing is asking, and again, this is for the boson system, not for the fermion system. Remember, when we put in this guy here, we assume the boson system. So we want to ask now is how does that mu vary with temperature? And there's a very subtle argument for it. Maybe it doesn't vary with temperature. Maybe it's a constant for a system that doesn't vary. Or maybe it does. It turns out it's going to vary. It's going to vary weirdly. Okay. So we want to work this out. And again, this is all the background before it's going to go naturally into the boson system kind of thing like that. Okay, so let's take a case here. So to do this, let's calculate the number of bosons in our system. Okay, so I'll start off our right hand. You tell me what comes on the right side of this. So let's start off. Okay, so we're in some state here. Okay, so the number of particles in that state is going to be the average number of particles of fermions are going to be. I was up at 3 in the morning grading my general physics. They had their test last night, so I wanted to get it back to them so they could grade it and so they could have it for their final. Because if all goes well, I'm planning to get my booster shot tomorrow. And I'm planning on being wiped out, whether I will or not, whether I can even get it tomorrow, I don't know. So I'm trying to get all my ducks in a row. Okay, so you're gonna have to watch me again today. So we said if we have an energy level, the average number of bosons in that energy level is given by.
It's going to be the integral of the Fermi, or not the boson sign.
Okay, so we're going to take the boson sign distribution here. It's a function of E. So that's the average number of particles in that given energy E. And then we multiply that by.
Multiply that by the number of states.
The number of states. Okay, so this is going to be the number of states. Of energy. We're going to write this in terms of our GE, DE, like we did before. That's the number of states, and then as you said, then we have to sum these up from 0 to infinity. Okay. Now we're going to assume that we have a particle with mass, and we're going to assume like a cubic box, so we can use our friend C e to the y half here. So if our bosons have mass. Okay, then we can say that this G of E and are not interacting, which we're assuming they are. Okay, we can say that this GE is that constant C, and I would have to go through and calculate what that constant is again. There's 2's and there's H bars and there's pi's and there's a V in there. And there's a whole bunch of things, none of which I remember. But I do remember the next part. How does it go with the energy?
E to the 1/2 or 3?
Good. 1/2. So we can put this all in here. So we're going to N equals this integral from 0 to infinity of 1 over e to the e minus mu over kVt minus 1 c e to the 1/2 dE. What I'm going to do is I'm going to take the c to the other side, and I'm going to kind of rewrite this. I'm going to write this as e over c equals this integral from 0 to infinity. I better make sure that that's still clear. And it is, yay! E to the 1/2 over e to the e kVt minus mu minus 1 dE. Make sense? Now here's the subtle part. Take the number of bosons over a constant. What would that equal mathematically? That is nothing but a.
That's a constant.
This is a constant. Which then means that this side of this integral over here, this must be a constant. Okay. For all. And what's the only thing varying in there? Temperature for all t. Right? So I can basically vary this temperature, what it doesn't matter what it is, and I always have to get the exact same thing here for a system. That makes sense? All right, this is where the problem lies, or the solution to the problem, depending on how you look at it. All right, so I'm going to rewrite this here. So the integral must be a constant. So we get this e 1/2. E, I'm going to split this into two pieces here. This has to go constant. So what we're going to do, we're going to let t go towards 0. It's not going to equal 0, but it's just going to get smaller. Okay. Well, maybe I'll just say smaller. Okay. So here's the problem. It tells us how to fix it. Okay, if this is the case, which is that term here? That term.
Or
Oh, it becomes larger.
Yeah.
So this term increases. So therefore, this term here must almost do to have our equality. We're always have to equal constant. That must decrease. Okay. And by this, I should say, when I say increases, I should say as t decreases, and this is as t decreases. Okay. So where's the problem here? We know that this mu is negative, so I can write this mu here. I can really write this mu as some minus the absolute value of mu. That makes sense? So what I really have in this guy here, this is really that's really this guy here. That makes sense? Okay, but as t decreases, naively, e to the mu over kVt increases. Unless, and what has to be the case there? So this shows you right here that mu can't be a constant. Now we're gonna get this to go down, because basically if this is going down here, this is gonna fall off. This has to get smaller. So the only way this can be is that this mu can't be a constant. Mu actually has to vary. What does it have to do?
It has to get smaller.
That's what's smaller. Unless this term here gets smaller. Okay. So in terms of make a little graph of this guy. And if I plot this mu here versus temperature, what happens is that this mu is going to be going like this. Is that as we decrease the temperature, this mu is going to decrease like that. That makes sense? Okay. Because again, this mu here is this minus this guy here. So this is getting smaller. So this is becoming less negative. Okay, so mu becomes less negative. As this T. Well, what can happen from this picture here? And we know that mu must be negative. Okay. So I can keep on decreasing this temperature. What do you think I can eventually make mu equal?
You can get it.
Kind of on the negative side of zero. So there's going to be some temperature. Okay, so there must exist some temperature called the critical temperature. Such that this mu goes to zero, and I'll put a little minus on here, meaning it's still negative, but it's zero, but it's okay. It's not zero; it's just on the negative side of zero. Okay, I think that's actually correct mathematics. We call this temperature Tc. So this temperature is T sub C. Yeah, as I said, that's so let's actually calculate this. Okay, so we have this guy here. So this is going to be at T equals Tc. This value here is going to be the C e to the 1/2 e to the e kT. The mu is now 0. Mu is 0. So I set mu equal to 0. Hey, you tell me how to solve that integral. I'll give you a hint, you're going to make a variable change, and then you use a friend.
Set e over kbt equal that, or set x equal to e over kbt.
Yep. Okay, so what? Oh, and you let me too. What did I say that T is? TC. Okay. So this is going to be E over KBTC. Okay, so our E is KBTCX. And so DE is KBTC. If we put this all in here, what do we get? We get N equals from 0 to infinity. The C. Okay, how many powers of actually? Let's pull out things. So I can pull out the C. How many factors of KBTC do I have?
3 halves.
3 halves. Okay, then left is the same, go from 0 to infinity. X to the 1/2 dx e to the x minus 1. This is a friend. Okay, what would that equal in terms of the other functions we have?
That's
Riemann zeta function of
Would it be 3/2?
3/2 going to go to n plus 1. So this is Riemann zeta function of 3/2 times the gamma function of
Times gamma 3/2.
gamma 3/2. I think when you work that out, that ends up being like 2.6 or something. I'm just going to leave it like that. Because, okay, I don't know what the C is well. So I'll just work out like that. So we have this n equals this C, Riemann zeta function 3/2, gamma 3/2, KB, TC. Ooh, nice to know. So we can actually calculate the temperature at which this is going to occur for the system here. Does that make sense? And the C here actually, I think, has a volume in it. So you take this over here, so you have the number density. So it'd be something you know about the system, because you wouldn't know the number of particles, but you would know the density of it, the number density. So you'd have something you can actually look up and calculate for this. Does that make sense? Okay. Now here's the problem. What happens if you go below TC? Unless we're the problem. Yeah, sure. So if you have our new graph here, here's your T. Everything's fine. We have TC. This is 0 on the negative side. And what does mu have to be?
It has to be negative.
Yeah, it must be less than 0. It can't go above here like this. Okay, so now what appears to happen? Let's go back and look at our. I'm going to put this over here. Okay, Bryce, when you watch this, you don't need the thing I put over there. I just wrote it over there. So when I erase the board, it's all fine. And are we still clear? We are still clear. So let's do the problem appears to come from, and then let's figure out how to fix it. So the problem is, remember we had this term over here. Okay. And this term here has to be a constant. Okay. So once we reach, and we know that once we reach TC here, this mu here basically goes to 0. Okay. And it can never be positive. So at some point, this is going to become 0. Right? Once you're at T equals TC here, this is 0. But if you go lower, you're not going to have this. What's going to happen to this term here? It's not going to be there. Right. And now this term then appears to have actually been vary, and this is no longer a constant. Okay, so what the problem is that when T is less than TC, the integral is no longer constant. Right, because this term isn't here, because you don't have this term here, this term here is not going to be 1. Okay. This is no longer here, so you just have this term here, and that's no longer a constant. And so there appears to be a problem. And here's the thing. Okay, we forgot something here. What did we forget in all this? I'll give you a hint. It comes from this guy here. What would this guy never include? It would never include the number of particles in the E equals 0 state. Right? As long as E is above 0, you can account for these right here. But if you have some energy equals 0 state, some ground state, okay, which we're going to call E equals 0, this one can never include it. So the problem, the GE C equals 1/2 term does not include the E equals 0 ground state. Because E is 0. Okay. So what we're going to have to do, we're going to have to put that in by hand. So we must place them. We must place this term in by hand. So what we're really going to have is basically an expression like this, but now we're going to have to actually include the 0 state. So let's actually see how we do this. So what we're going to have is that we're going to have this here. And then we're going to have basically, how do we put in that term? Well, this is going to have to be the Fermi-Dirac distribution here at 0, at equals 0. Then plus these others, then plus the other guy here. This is again, this is for T less than TC. And this is E to the 1/2 DE. E to the E over KT.
What about C?
I had to go to the bathroom, that's back. Okay, thank you. Okay. So what is this guy here? This guy here is 1 over E to the be 0, because that's your E. Now again, mu isn't 0, but it's really, really close to 0. So I'm going to write minus mu over KBT minus 1. That's what this term is here. Okay, then plus this other guy. This right here, this is the number of bosons in the ground state. Except equal 0. Okay, and this, remember, mu is really, really tiny. So if mu is really, really tiny, okay, what can I do with the exponential?
Expand it.
Taylor expand it. So let's do that. So this is 1 over, well, what does that become? We Taylor expand this guy. The exponential goes to 1.
Minus.
Okay, so it's plus
Yeah,
then the
plus
x
the
term,
negative. Yeah.
which is this guy here. Let's start the top. We're not going to have to worry about the other terms because they're going to be a lot smaller compared to this term. Because again, the mu is on the negative side of 0. Then minus 1. Okay, plus the integral term. So this right here, this is really the number of particles in the excited state. Well, what does this term here become? Well, this one cancels that one here. I can flip this up. So this gives me n equals this kBt over mu minus sign here, plus then this guy right here. That make sense?
Mhm.
Okay. So what's going to happen here is that as your temperature decreases, okay, what happens to this term here?
That blows up.
And this term here becomes really, really large
The
in the bottom.
goes to zero.
And so you're going to basically have this over something large. So this is going to go to 0. You're going to have almost no excited states. So instead, what happens? C goes small. What does this mu do? It becomes actually, it's really, really tiny. Okay? And actually, this term becomes large and down. So what's going to happen is that once you actually go below that T equals TC here, you actually start having macroscopic occupation of the ground state. And that is what you call a Bose-Einstein combination state. So once T is less than TC here, you have macroscopic, meaning a large fraction of the particles. Occupation. Of the ground state. This is called a Bose-Einstein condensate. Again, Einstein predicted this early on, but there's no way to do this. Now, when you do this, there is an assumption here. When you work out this, we assume that you have non-interacting bosons. Okay, and you could say, so sometimes people will say that helium-4, so often people, meaning physicists, and most people, will argue that helium-4 in the superfluid state is a Bose-Einstein condensate. The reason why that's technically not true is that helium, these molecules actually interact. Now, obviously, this plays a certain role in it. So, I mean, it's certainly Bose-Einstein condensate-like. So it's similar to it, but it's not exactly because of the interactions. Okay. And the reason why you'd have a superfluid, remember, a superfluid means it's going to be a fluid that basically flows without any viscosity. And again, what does viscosity mean? Viscosity means it's an internal friction. So the part of the system's losing energy. Well, if you're in the ground state, how much energy can you lose? You can't, because you're in the ground state. There's no energy to lose. So once you flow, you flow. There's going to be nothing to stop you because there's nowhere you can use your energy. And that's the Bose-Einstein condensate. And that's a super. Okay. That's kind of neat. Now, we're the ones that is actually that group in Boulder, Colorado that produced it. What they did is that how'd you get non-interacting particles? What would you want the density of the system to be? Low. You want a low density system, and you also want you basically want inert gases, so like argon, xenon, things like this. And so what they did, they basically figured out a way of taking a noble gas. And basically what they could do is that they could get rid of the really fast moving particles by a technique referred to as laser cooling. This is really quite ideal. And there's a lot more to it. And besides that, you basically let the fast moving particles get out. So what's left is actually colder. And you can basically have a very low density. So they're going to be non-interacting. First of all, they're already noble gases, so they don't interact well. And if you have a low density, then they're really not going to interact. And so that's how you get the non-interacting particle, and then you can use this evaporative cooling technique to cool the system, and that's how they produce the Bose-Einstein condensate. There's a lot of technologies that went into that. This is absolutely brilliant. I heard a talk on it, several talks actually. But did it too. So it's actually quite amazing. That makes sense? Now we can do more though. Okay, so is there any question about that part? Okay, so what I want to do is I want to calculate kind of the fractions here. Let's get the fractions down. So let n sub e equal the number of bosons in the excited state. And you'll let n sub 0 equal the number of bosons in the ground state. And what I want to do, I want, so we know that n, the number of particles, equals n0 plus n sub e. And I want to figure how these actually vary when you below TC. So how do NE and N0 vary when T is less than TC? This is going to be preposterously simple. Okay. So, tell me how to calculate that. How do you calculate that? If you, again, we're below TC. Okay. So how do we calculate the number of excited bosons? Got too much sugar. They're all excited. They're waiting for Santa to come. We do that calculation we did before. We're going to have this from 0 to infinity, C e to the 1/2 dE equals e to the e. Now, why can I set the chemical potential equal to 0? Because we're below this T equals TC. So this is 0 here. This is going to be over KBT minus 1. Well, hey, what is that? How do we solve that?
You do a change of variables. And
Yeah, we're gonna basically let this x equal e over kbt. Well, we did this before, except we had a TC here, so it's the exact same result as that result over here. So you know that this n sub b, when you do this, is that going to be that constant, a Riemann zeta function of 3/2, a gamma function of 3/2. Okay, my Riemann zeta functions and my gammas are looking a little too closely. Gamma. Okay, times your KB. Now this is just T to the 3/2. So now what I can do is I can divide this by the original one. Divide this by the n expression when T equals TC. So if we do that, NE over N. Okay, so I have the C, Riemann zeta function, hams, gamma function, hams, KBT, all divided by C, Riemann zeta function, 3 hams, gamma function, 3 hams, KBTC to the 3 hams. So what I'm left with is this NE over N equals T over TC to the 3 power. Make sense? So your N here, N sub B is N T minus TC to the 3 power. Okay, so what do we know? We know that the number of particles has to equal the number of particles in the ground state plus the number of particles in the excited state. So this has to be N minus NE. I put in my friend here. Shazam, I'm done. Okay. So we should make a graph of these guys. Your number of particles in the excited state looks like this. Okay. And so this is your NE and N0. Okay. This right here is going to be your N. And this guy, so this is your NE guy. And then this guy goes like this. This is your pinnacle. And then basically once you get past here, then it just flattens out like this. Because you don't get any more particles. They're all in the excited state. Okay. Hey, let's calculate the heat capacity of this. And this would be below. Let's see here. How do you do it? CV is what?
CV is partially your substitute.
And this is DVT. That means we need U. Hey, you tell me how to find U. I'm right here.
Integral 0 to infinity E Bose-Einstein.
Bose-Einstein, e to the E over KBT. Again, I'm below T equals GC, so my U is 0 minus 1.
Times GED, which is C to the 1/2.
So C e to the 1/2 DE. C integral 0 to infinity e to the 3s power E. Hey, how are you going to solve that?
Same trick again.
Same thing again. So we're going to let X over KBT or E is KBT X, so DE, KBT DE, and DX. So I'll pull out the C. How many fractions of KBT do we have?
3/2.
KBT
Squared.
KBT. We get a 3/2 from this guy. We get another one from this guy.
5/2.
So the 5/2. Then an integral from 0 to infinity of this x to the 3/2 dx e to the x minus 1. Okay, what would this thing be?
Riemann zeta 5/2. Yeah.
So this is the Riemann zeta function of 5/2 times gamma function of 3/2, 5/2. Okay. So we don't. So what we're going to have? We're going to have this C times Riemann zeta. 5/2 So this is really a constant. That's a constant thing.
You forgot KB.
What?
You forgot KB.
Yeah. KB here. Okay, so what does it mean as far as just formally then what's going to happen here? The CV has to go as what power? Take the derivative here.
It has to go T to the 3 halves.
Yeah, this is going to have to be T to the 3 times power. What happens here is if you do this, make a graph of this. This is T, here's your TC. This is going to go like this. This is your proportional to T to the 3 power. What happens is if you work out the other parts here, then this kind of then there's a discontinuity in the energy graph like that in the CV. Okay. So this Bose-Einstein condensate condensation is a phase change. And here's the big difference on it. Okay, we talked about phase changes before. I should say phase transition instead of change. It's the same thing. So phase transition. Okay. So we mentioned this before. What did we say? Almost all phase transitions. Where does the physics of that come in? We looked at a function very early on in this course. We looked at F. We said our Helmholtz free energy is by definition what? U minus
TS.
TS. And we know that nature tries to minimize F. We said there's different ways of doing it. You can either minimize F by minimizing U, okay, or you can minimize F by basically increasing S. So basically, nature trying to minimize this function, there's different ways of doing it. I can either have a state with a low U and kind of a very low U, or low entropy. That's one way. And that would be like an ordered state, like a solid. Or I could actually have a really, really large S, and that'd be a case of a gas or a liquid. So normally you get phases by nature trying to minimize this function. That's what causes phases. With one exception. The only exception, as far as I'm aware of, is actually this phase. Well, there's probably some weird stuff with corporal plasma as well. Is this guy here, this phase transition. This phase transition here is not governed by that expression here. This is entirely governed by quantum statistics. So this right here is a unique feature. So there would be a big but here. But this phase transition is governed by quantum statistics, meaning the nature of being a boson. And not by minimizing F. There. I've now officially done everything that I feel like I'm obliged to do. We should have just one more class to do something you're not obliged to do. Okay. I don't know what that'll be yet. But we'll have a lecture on Friday. Again, I maybe if I do get the if I seem off on Friday, I'm hoping again, as I said, to get the booster shot tomorrow. And most people seem to have 24 hours of left. So if I come across as it's going to be because that's how I feel. So also question for this. It's actually quite beautiful. Okay.